In this module, you will learn about the crystalline structure and conduction of an electric current in intrinsic semiconductors. A semiconductor, without any artificially added impurity, is called an intrinsic semiconductor. Both silicon and germanium, the two most commonly used semiconductors, exist as intrinsic semiconductors. Let us take a look at the atomic structure of silicon and germanium. Both silicon and germanium have 4 valence electrons. In crystalline form, each silicon and germanium atom uses its valence electrons to form 4 covalent bonds with 4 surrounding atoms. Let us use the crystal structure of silicon to further study intrinsic semiconductors. Remember, the following discussion applies equally to germanium in its intrinsic form. At absolute zero, all the covalent bonds in the crystal lattice of an intrinsic semiconductor are intact. Thus, at absolute zero, there are no free electrons to occupy the conduction band, and the intrinsic semiconductor behaves like an insulator. However, at higher temperatures, some electrons gain enough thermal energy to break free of the covalent bonds in the crystal lattice. These free electrons move to the conduction band, and the material starts behaving like a semiconductor. Note that each electron that moves to the conduction band leaves behind a vacancy in the valence band. This can be visualized as breaking of a covalent bond, where an electron becomes free and leaves behind a vacancy in the covalent bond. An electron breaking away from a covalent bond takes away a unit negative charge with it, leaving behind a vacancy with an assumed unit positive charge. A vacancy with a unit positive charge in a covalent bond between atoms of a semiconductor is called a hole. Thus, whenever a covalent bond is broken in an intrinsic semiconductor, a free electron and a hole is created. We refer to this as an electron-hole pair. Hence, in an intrinsic semiconductor, the number of free electrons is always equal to the number of holes at any given moment. Consider a hole or a vacancy at position 1 in the crystal lattice of a semiconductor. Now, an electron from position 2 can jump to occupy the vacancy at position 1. This fills the vacancy at position 1 but creates a vacancy or a hole at position 2. Similarly, an electron from position 3 can jump to occupy the vacancy at position 2. This fills the vacancy at position 2 but creates a vacancy or a hole at position 3. As a result of such jumps of electrons across covalent bonds, the holes or vacancies appear to move across the crystal lattice of a semiconductor. Note that the movement of holes occurs because of the movement of electrons across covalent bonds in a semiconductor, and not because of the movement of free electrons. Thus, there are 2 types of moving charge carriers in the crystal lattice of a semiconductor: the negatively charged free electrons and the positively charged holes. When an electric field is applied across a semiconductor by connecting it across the terminals of a battery, the free electrons move towards the end connected to the positive terminal and generate an electron current denoted by IE. the holes shift towards the end connected to the negative terminal and generate a hole current denoted by IH. The total current flowing through the semiconductor is equal to the sum of the electron current and the hole current. If a free electron collides with a hole, it fills the vacancy in the covalent bond without the generation of any other hole. This is called the process of recombination. Under thermal equilibrium, the rate of generation of free electrons and holes in a semiconductor is equal to the rate of their recombination, so that the density of charge carriers in a semiconductor remains constant. You have now reached the end of this module. In this module, you have learnt that a semiconductor without any artificially added impurity is called an intrinsic semiconductor. In crystalline form, each silicon and germanium atom forms 4 covalent bonds with 4 surrounding atoms. At absolute zero, all the covalent bonds in the crystal lattice of an intrinsic semiconductor are intact. No free electrons are available and the material behaves like an insulator. Removal of an electron from a covalent bond creates an assumed positively charged vacancy in the covalent bond called a hole. In an intrinsic semiconductor, the number of free electrons is always equal to the number of holes at any given moment. The total current flowing through a semiconductor is equal to the sum of the electron current and the hole current.